So in this session, we will discuss about how to write test bench for the Verilog code. So once if your design is completed, okay, if your design block, for example, half adder, full adder, multiplexer, 4-bit full adder, okay, once a design block is completed, it must be tested. So the functionality of the design block. So the functionality can be tested by applying the test vectors, that is called stimulus. By applying the stimulus, and you have to check the results. Okay, so it's a good practice to keep the stimulus and the design blocks separately. So the design blocks code.b file and the test bench code keep it separately. So the test bench are stimulus block, both are same. Okay, the stimulus block can be written in Verilog. So separate language is not required for the testing. Same Verilog code is used for writing a test bench also. Okay. So the stimulus block only is called test bench. So different test benches you can create for the design blocks. There are two ways. Okay, there are two ways to write the test bench. To write the stimulus block, to write the test bench. In the first style, okay, in the stimulus block or the test bench block, you have to instantiate the design blocks and directly you can drive the signals to the design block. Okay, so the stimulus block, the test bench becomes the top level block. It manipulates the signals and it checks and it displays the output signal. Okay, so the first style of testing the design. So this is the stimulus block or test bench block. Okay, so this is your design block. This is your design block. Okay, this is your stimulus block. This is your stimulus block, or stimulus block is nothing but test bench. Okay, so this stimulus block instantiates your design block and directly drives the signals, and you can verify the output. So the design blocks becomes the top model, top level block. In the top level block, so the stimulus block instantiates the design block and directly drives the input signals to the design block. Okay, so it manipulates the signals. So the design it manipulates the signals and it checks and it displays the output signal. The second style is you can apply the stimulus. You have to instantiate both. The second style is you have to instantiate both the stimulus block. This is stimulus block and your design block. Design under test. The design block. This is your design block. The design block may be a ripple carry adder, for example. Combination circuits will take. So here the first way of writing the test bench, the stimulus block instantiates the design block and directly drives the signals in the design block. Okay, so the stimulus block is the top model. So it will manipulate the signals and it will display the output. The second level of the second style of writing is you have to apply that means stimulus to instantiate both stimulus block and the design block in a top level. This is a dummy model, top level model. This is a top level model. Top level model. So the stimulus block interacts with the design block only through interface. The stimulus blocks interact with the design block only through the interface. Okay, only through the interface. So now the stimulus block drives the signals. For example, it may be a counter or 4-bit adder. Okay, so A, B, for example, sum, carry, sum, carry. So feed the data. The stimulus block drives. Okay, the stimulus block drives the signals which are connected to the signals of the design block, and it also checks and display the signal okay, which is connected to the signal. So the and display, for example, this is inside A, B, sum, carry. Okay, understand? So in the second style of writing the test bench is you are instantiating both stimulus block and the design blocks in a top level dummy model. Okay, through the interface. So now the stimulus blocks drives the signals, okay, which are connected to the design block, and it all checks and it displays the signal. Here it displays the signal. Okay, this is one way of writing a test bench. Sorry. Okay, now we'll write the test bench. Okay, or you can say it's a stimulus block to check whether the our design block code of adder or full adder, 4-bit full adder is functioning correctly or not. Okay, and we'll see the waveform. Okay, the stimulus will create the waveforms. So at this stage, you no need to worry about all the syntax of the that is a what are the constructs in the Verilog HDL. No need to worry about that. So here we are going to design a design block. Only simply concentrate how the design block is instantiated in the test bench in the stimulus block. Once the stimulus block is completed, we will run the simulation and you can verify the functionality of the design block. So what are the outputs you are obtaining when stimulus and the design blocks are simulated? So how you are getting the output? So when the stimulus data test bench and the design blocks are simulated using this tool. Getting or not? So again, don't worry about the Verilog syntax at this point. We are writing a stimulus block for our design, and once the stimulus blocks test bench is completed, we are ready to run the simulation and verify the functionality. So the output obtained, what are the outputs are obtained when the stimulus block and the design blocks are simulated. So for that, I'll explain the test bench how to write. Already we written the test bench and Verilog code files are created. So go to file, open project. In the combinational circuits. So already we created the design block. We have created, for example, FA, DF, and full adder also we have created. Half adder, full adder, and the test bench for full adder have created. 4-bit full adder, we didn't try this test bench. So if you see the coding for 4-bit full adder, so this, for example, we'll write the test bench for the 4-bit full adder finally. So 4-bit full adder, here in the 4-bit full adder using structural model coding we have written. This is a design block. Model name, output followed by the input, then declaration of the output ports and the input ports, and declaration of the wires. So here remember that what is the hierarchy we followed for the port mapping, output followed by the inputs. Then we have instantiated, okay, we have instantiated the full adder, 4-bit full adder using single bit adder. So for example, if it is a 4-bit adder, you are instantiating the single bit adder 4 times. Like subroutine, okay, we have written the frequently used single bit adder separately the design block. In the 4-bit full adder, we have instantiated 4 times and following the port mapping rules, so outputs followed by the inputs. Okay, this is a design block. Now we'll create a test bench code. Okay, for this, we'll create a test bench code. That is a stimulus block. Test bench or stimulus block using Verilog HDL, we create a source. Then we will simulate both test bench, stimulus block and design block. Okay, so first we'll create the test bench for the 4-bit full adder. So now new source. So Verilog test fixture. I'll give what is the file name I given here, 4-bit. So okay, 4-bit full adder fa underscore tb. Let us have a file name 4-bit full adder underscore tb. Test bench, you have to understand. So next, so you select this 4-bit full adder, which for which source file are going to create a test bench for the structural modeling of 4-bit full adder. So you select this one. If you are writing a test bench for half adder, you select this one. If you are writing a test bench for full adder, single bit full adder, you select this one. Now we are going to write a test bench or stimulus block for 4-bit full adder. So you select this one. Then next. Then now if you see the description, source type Verilog, source name the test bench, okay, it is associated with the structural. So this is all you have to check. Then finish. So now we'll create a test bench for the 4-bit full adder. Okay, we can remove the comments line. So simply you can give / test bench. That is a stimulus block. You can say stimulus block. Test bench. Okay, what is a test bench? You are verifying the functionality of the design. Okay, test bench for 4-bit full adder. So we are going to write the test bench or stimulus block using Verilog HDL. At this stage, no need to worry about the so many constructs. Whatever we are using here, I'll explain. Okay. So here, so do you want to say this first before coming? Yes. File name. So now apply the stimulus. Apply the stimulus or you can say it is a test vectors. Stimulus, that means test vectors. Test vectors. Stimulus are nothing but test vectors. So apply your stimulus to the design block. You have to instantiate the design blocks and apply the stimulus directly to the design block and monitor the outputs. Okay, design block and monitor the outputs. So if you notice here, so the test bench created for the 4-bit full adder. So in the test bench there is no IO port terminal list. Remember that there is no IO port terminal list. So here you have to instantiate the only the design and the test. This is our 4-bit full adder structure. This is your design block name. So instantiate the design block. Instantiate the design block. Instantiate the design block. Here the name is 4-bit full adder underscore str. Okay. So module name, test bench name. There is no IO port declaration here. Then you have to declare variables here. Declare the variables. So if you notice here, declare the variables to be connected to inputs. So the commands are very important to understand the concepts. Module name, test bench name. There is no IO port declaration. Then you have to declare the variable, okay, to be connected to the inputs. So what are the inputs? A and B, C in. So you are declaring the variable in order to store and verify the results. So declare the variables. So reg is a variable. Okay. So all the inputs are declared as reg. Similarly, outputs. Declare the outputs as wire. Declare the outputs as wire. Declare the outputs as wire. Okay, these two command statement. Understand? Module name. Here you can say test bench created with the module name without specifying the IO ports. IO ports without specifying the IO ports. Okay, so there is no IO port specification here. Then second, you have to declare the variable to be connected to the inputs ABC as a reg. Declare the variable here reg, bracket reg. There is a variable keyword to be connected to the inputs. Okay, then declare the outputs as wires. Then you have to instantiate the design block. This is a stimulus block. Actually, this is a stimulus block we are creating. In that, you have to instantiate the design block. Okay, that is a unit under test. Then instantiation. Then you have to stimulus the here if you see stimulus test vectors. Stimulus the inputs. So what are the for 4-bit full adder for example? So once the design block is completed, you have to the design must be checked. The design must be checked by applying the stimulus or test vectors. Okay, for the 4-bit adder, we can apply some only few combinations and we can monitor the results. Okay. So here the stimulus is a top level model. Okay, the stimulus block is a top level model. This is a stimulus test bench as a top level model. Okay. So okay, I hope that every model step by step the clarification is required. So now we are instantiating our design block and applying the stimulus and drives the design block. Okay, by applying the stimulus and check the result, checks, and it will display the result. Okay, so these are the what are the inputs and outputs of your design under test. Now stimulus the inputs. Okay, we'll concentrate how to give the stimulus inputs for the 4-bit full adder. Okay, and we will monitor the signals. So initial, here you can use monitor also. So we can monitor the signal. Okay, so that for that we can use a system task function $sign monitor, which is also used to display the signals when they changes the values. Okay, now we'll feed the data. So initial, so for multiple statements you can use the begin and end. So initial, here stimulus the inputs. So before this initial, okay, initial, begin, we can use the monitor to display the signal. System function monitor, the syntax, open the bracket, the system function simulation and the simulation time. So the string, we are displaying the string, getting the values of for example, this is a display command only, a, okay, a, for example, we are giving a, okay, this will give a is equal to small cases you use, otherwise uppercase also you can use a equal to percentage b, okay, comma b equal to percentage b, comma c in equal to percentage b, comma, we'll get the output c out, this sum is equal to percentage b, comma, sum, comma, c out, we use c out, c out equal to percentage b. Okay, so you can, that every new line you can specify the backslash n, then close the string. Okay, then comma, pass the arguments. So what are the arguments? A comma b comma c in comma and sum comma c out. Okay, so close the bracket, end with a semicolon. So again begin end. Okay, so stimulus, so here we are, there is not a inputs, we are setting up the, so we are setting up the, so you can say this is a setting up setup, otherwise you can set up the monitoring for the signal values. So by using this display command s monitor at simulation time, get the value of a b c in, and okay, here dot mode, and display the output sum Okay, sum and sum, comma, C out. Okay, A, B, so arguments A, B, C in sum, C out. Then it stimulates the next command, stimulates the inputs, stimulates the inputs. Here you can learn that how to use the language constructs of Verilog HDL for giving the stimulus values or test vectors. So for that you have to stimulate the inputs. So initial, begin. So we can give A, so 4-bit number, no? So 4-bit apostrophe. So single bit, okay, no problem, but it is a 4-bit full array test bench. So we have to feed 4-bit A value test vector. So you can represent either binary. So you can represent binary 1010. Okay, like that you can specify, or if you want to specify in decimal number also you can specify. Okay, for example I'm giving t t for example 3. Okay, that also you can give. So decimal representation you can do. Then so b, so this is a b is equal to, again I can represent 4, the number of digits 4 apostrophe. Okay, so decimal representation I can do some d value 3, no, so 2 I can give decimal representation or binary representation. Then c value, c is a, not c is a 4-bit, c is a scalar single bit, so you can say 1 bit, so 1 bit apostrophe b, I can initialize c in 0, so c in 0. Understand, here you can learn this language constructs, how to initialize the inputs. Okay, so A, B, both are 4 bits. So in decimal representation, I given 3, 2. Initially, C in is 0. So it's a single bit scalar bit. So I'm giving 0, binary bit. Then after some delay, so that is used by hash. After some delay, so 20 we can specify, or 50 we can specify 50, 50 or 100, whatever. Okay, we'll set the duration you can specify. Then so here after some delay you can change the value of a and b with a different value. It will see me. So now I can give some of the data. Okay, here I can give 2, 2 I can give, and 4 I can give. Scene I can give as 1. So scene is 1. Okay, so scene is 0. Okay, no problem. And again after some time I can. So what are the different possible combinations of test vectors you can give? In the previous case, then half adder, full adder, or 2, for half adder only 2, 2 to the power 2, 4. But in full adder, 3 inputs, 2 power 3, 8 combinations, we given all the test vectors we given. Here 2, 4-bit, 2 power 4. So no need to feed all the combinations. Some input combinations you can give, and you can monitor the outputs. So we can simulate both the stimulus block, test bench block, as well as the design block. Okay, so now we can the next control CV after, so we can give decimal number, uh, for example decimal number 15, 15 also I can FF. Okay, 15 I can give, otherwise 10 I'll give. Okay, then B number I can give 15. B can be given as 15, 10 and 15. Okay, 10 and 15. In that case, this I can make Cn is equal to 1. Okay, so some test vectors again, control CV, again after some delay, I can change the data. So the decimal representation 5, and here I can give 3. Okay, so maybe 0 or 1. So with some input combinations I can check. Then begin, end. We have to substitute here end. Then you have to finish. Okay, then end mode. So we have written the test bench. So we have written the test bench and save some unexpired token, line 39, line 39, hash symbol. Okay, begin, end. This end is not required. This end is sufficient. Now, again, where is it? Hash. So I written the complete test bench for the 4-bit full adder. This is my top level model test bench model, and this is an instantiation of a design block under the test. Then in order to monitor the values signal changes, so I can use the display command, monitor command, system task function, then apply the stimulus, uh, different in some input combinations I given here. Now we'll save and simulate both design as well as test bench. Okay, for the simply simulate behavioral model, you can verify the output. Okay, see this window, you can see some. So all the you can move the cursor. Okay, you can move the cursor here. You can see the data. For example, A, B. So A and B is given. So what is that? C in is 0. So 1 1 0 0 0 1. So carry C out is 0. So similarly, you can keep the cursor here. So I think the delay specification we can change 100. Okay, close this window. Close this window. Here I can change 100. 100. Okay, now you simulate. Yes, want to save. So I can see the waveforms here. I can move the cursor here. I can verify the values. So I can move the cursor and verifying the result. You can give the different combinations. Okay, the last one, for example. So C in 0, for these values, you are getting C out is 0, sum is 1000. Okay, so now hope that completely understood about the test bench. Then why we are writing the test bench in order to verify the functionality of your design. For that, we have to write a top models test bench stimulus block under which you have to instantiate the design block, then driving the signals, input signal stimulus, the inputs, and checks the results and display the results. So both the design block and stimulus block simulated and verify the output waveform result. Okay, so hope you understood everything. So kindly explore the uh, design block and the stimulus block test bench for this next experiment multiplexer. So here So for the sessions covered, half adder, full adder, 4-bit full adder, how to write a test bench, then how to validate the test bench, okay, how to validate the design, everything we have covered in this session. So next session we'll discuss about the other digital circuit designs. Thank you.